This is the second section of linear transformations, and here we're going to look at reflections and rotation. So our job now is to have a transformation, or maybe a diagram like we've got here, and write down the matrix that it represents, or represents the transformation, or even we should be able to, by the end of this, look at a matrix and say what that matrix does. Does it do a reflection, rotation, enlargement? Okay, we should be able to try all of those things. Now, how are we going to do that? Well, what we do is we are going to look at where the points 1, 0 and 0, 1 go. Okay, so we're going to see where the points 1, 0 and 0, 1 and see where they map to. So where do these map to? Now, why those 2 points in particular? Right, let's have a look. So T is going to represent the transformation matrix that I'm trying to find. Okay, and I'm going to transform or move these points 1, 0, 0, 1. Okay, so maybe I know where these points move to. Yeah, so I know where they're moved to. So this is the image. This is where they've moved to. And I know the points that I've started with. I want to find a transformation. Now you should recognize this matrix here. This is the identity matrix. Now if this is the identity matrix, actually we've got this. T equals A, B, C, D, where the points have moved to. So that's why we look at where the points 1, 0 and 0, 1 have moved to. And you can see it on this diagram here. Yeah, I've got the points 1, 0, which is this point here, and 0, 1, which is this point. If I can see where they've moved to, then that is the transformation matrix. Now we need to know where each point has gone. So for this one here, I need to know whether it's moved to this one here, -2, -1, or whether it's moved to this one here, -1, -2. So when we do our diagrams and do our working, we need to know which one goes with which. Otherwise we'll get the wrong type of transformation. So for example, on this one here that we've got, if 1, 0, if this point, let's say, ended up here, so 1, 0, the first column in this matrix, let's say it's ended up at -1, -2. Okay, so I'll write that down. So I'll just take that out, AC. So this is going to be where 1, 0 has gone. So if we say that it's gone to that green line that's at the bottom, it's gone to the point -1, -2. So let's write that down. -1, -2. And if I look at the other point, which is 0, 1, this one, which is the second column, where does this one go? So let's say we knew that this one went here, then that is -2, -1. Okay, so let's put that in. -2, -1. So that would be the transformation matrix there. So we use the points 1, 0, 0, 1 because it's basically the identity matrix. We could use any points we wanted to see what the transformation is, but this is the easiest way to do it. Okay, so we've got a transformation U represented by the 2 by 2 matrix Q, which is a reflection in the y-axis. Write down the matrix Q. Right, so this is what we do. We draw a little axis like this. Okay, I'm going to use a thick highlighter like this. Okay, this is going to represent that 1, 0. So this point here. So this is the number 1 here. And in a different color. Yeah, so let's get the highlighter here. So in a different color here. Yeah. This is going to represent 0, 1. Okay, let's put that there. So that's the point 0, 1. And I want to see where those points have gone. Now, if it's a reflection in the y-axis, I'm going to do a fresh diagram here. Now, if it's a reflection in the y-axis, the green arrow doesn't move. So I'm going to keep it in green and keep it there. So this is a reflection in the y-axis. Now, what happens to the blue arrow? That actually flips and goes this way, like this. Now, so what's happened here? That is still 1 here, and this one is now -1. So if I want to write down the matrix Q, I just need to write down the coordinates of these points. I look at where 1, 0 and 0, 1 have gone. Now I've color coded them because the order in which we do them is important. Now the blue arrow would be in the first column because that's the 1, 0. So the blue arrow in the second diagram is the coordinate -1, 0. So the blue arrow, which represents my 1, 0, which would have been in the first column of the identity matrix that we're using to help us do these questions, must match up where that one goes. So it's useful to do these things in color so you know which one is which. And the second column is going to be the green arrow, which is 0, 1, and now 0, 1 has ended up, well, it stayed at 0, 1. So here I have the transformation. This tells me what I need to do to any point for it to end up as a reflection in the y-axis. Okay, part B. Write down the equations of 3 different invariant lines of this transformation. Just as a reminder, an invariant line, and we can have invariant points as well. Invariant line is a line that doesn't move under a transformation. Doesn't move under a transformation. Now, for any linear transformation, the origin is always invariant. Yeah, that will never move. But we want 3 lines that don't move if you reflect them in the y-axis. So for example, if I drew a line here, that line won't move if I do a reflection in the y-axis, and that line is the line x equals 0. So x equals 0 is invariant. Okay, are there any other lines that don't move? Well, this line won't move. Yeah, it will look like it's staying exactly where it is. So we can say that the line y equals 0 is invariant. In fact, scrub what I just said. That wouldn't be true because points on one side of the line would reflect to the other side of the line. So that's not quite the case. So I actually think there's a mistake in this question, that this shouldn't say 3 because there aren't 3 different lines. There's only one, and that's the line x equals 0. So I'm going to change that. I think that's meant to say the. Write the equation of the invariant line of this transformation. If you think it's different to that, put a comment below and you can correct me on that. But as far as I'm concerned, the only points which don't move are those points on the y-axis. If we're reflecting in the y-axis, everything else is going to get flipped across. Okay, here we've been given a matrix. Describe fully the single geometric transformation U represented by the matrix P. Right, so let me just draw like a little grid to help me out with this. So let's have red here, and let's have green here. Right, so these are the original points. And now what's happening? So the first column is going to be where the red one goes, and that ends up at 0, -1. So 0 across 1 down. So that means that the red arrow ends up here. So the red one would be in the first column, and that's in the first column of this transformation matrix. The second column is -1, 0. So that's going to be where the green one goes. So -1, 0 is going to be here. So what I now need to work out is, well, what is going to move that green and red point round to the new green and red point? Now, the only thing that it can be, it can't be a rotation, because you can see that all of the colors would be different. The green would be down at the bottom if it was a rotation, so it's not a rotation. So it's got to be a reflection. So we just want where their mirror line is, and it looks like the mirror line is here. So that's a reflection in a line y equals -x. So reflection, and we need to fully describe it, so we don't just say reflection. We need to give the equation of a mirror line. Reflection in the line y equals -x. So that's part A. Okay, there's a box here that gives us some general transformations, matrices which you can remember, but I find it easier just to work them out rather than try and memorize these. Part B, given that U maps the point with coordinates AB onto the point with coordinates 3 plus 2AP plus 1, find the values of A plus B. So what it means is this transformation matrix 0, -1, -1, 0 transforms these points AB. Okay, and they end up at these points here, 3 plus 2A and B plus 1. So now it's just a matter of turning that into an equation and solving it. So we'll get 0A minus B. Okay, so from the top row, 0A minus B, or so negative B, will equal 3 plus 2A. And from the bottom row, you'll get -A plus 0B, or just -A, equals B plus 1. So now all we do is to solve these simultaneously. Yeah, so let's, well, we've got them written as equations. So what I could do from the second equation, I could rewrite that as A equals -B minus 1. I'll substitute that into the first equation. So I'll have -B plus equals 3 plus 2 times A. So it's 2 times this, -B, -1. So from there, that will give me -B equals 3 minus 2B minus 2. So from that, we will get, if I add 2B to both sides, I'll get B equals, and then I'll have 3 minus 2, so I've got B equals 1. Now all I do now is to substitute that back into maybe the bottom equation. So -A equals 1 plus 1, okay, which means -A equals 2, which means that A equals -2. So we found the values of A and B. Right, so we've got a different transformation here, and it's a rotation of 180 degrees about the origin, and there are always going to be rotations about the origin since we're only dealing with linear transformations. And what we need to do is write down the matrix P. So we're going to do the same thing that we did before, which is to look at the points 1, 0, and I'm going to use red and green. So red will be that one. 1, 0, 0, 1, which is that. And if it's a rotation of 180 degrees about the origin, let's draw where 1001 will end up. So rotation of 180 degrees will mean that the red one moves around 180 degrees to the other side over here. And the green one rotated 180 degrees is going to move down here. Now remember, the red goes in my first column, the green goes in my second column. So the matrix P is going to equal, so the red goes in the first column, which is negative 1, 0. The green goes in the second column, which is 0, negative 1. So there we go. We've got a matrix that represents a rotation of 180 degrees. Now part B, we need to show that the line y equals 3x is invariant. In other words, it doesn't move. So let's write this down. The line y equals 3x. Now if I can show that any point on that line doesn't move, I show it's invariant. So we can't just pick a point like, I don't know, 1, 3 or 2, 6. We need to pick a general point. So what we want is a general point, which could be any point, on the line y equals 3x. So I can't use numbers. So if I say that I pick the x coordinate to be something like k or any other letter, that means that y is going to be 3k. So the general point on the line that I'm going to pick is the point k, 3k. Yeah, and I want to see what happens to k, 3k. Does it end up as another point, which is like k, 3k, like 2k, 6k, something like that, or does it end up as something completely different? Well, let's have a look. So let's do a transformation. So negative 1, 0, 0, negative 1. Let's do a transformation of the points k, 3k, a general point. Don't just pick one, pick a general point, because picking it for one point only proves that that point is invariant. We want to prove that any point is invariant. So if I do that, multiply it out, I'll get negative k plus 0 times 3k, so we don't write that down, it's enough to write down, and then 0 times k, and which is 0, and then minus 3k. Now if we have a look, a point k, negative 3k is also on the line y equals 3k. Okay, so the point negative k, negative 3k is still on the line y equals 3x. Yeah, it works, because if you put negative k, negative 3k in there, that equation still works. Yeah, so you could have negative 3k equals 3 times negative k. Yeah, so that proves that the line is invariant under this transformation. So the line y equals 3x is invariant under the transformation P, because we're using the letter P. Right, okay, so we've got another transformation here. We've got some funny looking square root things. So we're going to do the same type of thing. We're going to describe what this transformation does. So again, start with our points 1, 0, 0, 1. So I'm going to use red and green, just like before. So red here and green here. Okay, let's look to see where they go. Right, so the first column, I've got these points. One is negative root 2 over 2, and then root 2 over 2. So they're going up at angles. They're not exactly like on the axis this time, not a problem. But what I do notice is that if I put these numbers on, so let's put negative 2 over root 2, oh sorry, no, it's root 2 at the top, negative root 2 over 2 for that one, and this will be root 2 over 2, down here would be negative root 2 over 2, and this point here will be root 2 over 2. So we can see they're going up at like 45 degrees. So the first one has got a negative x coordinate and a positive y coordinate. So the red one ends up going up here like that, and the green one, well, they're both negative, so that ends up going down here. So I can see that this is a rotation of 135 degrees. That's anti-clockwise about the origin. Now you might think to yourself, right, is there another way that I can do this without having to rely on trying to draw a diagram? Okay, yes there is. Since we are told that this is a rotation, all rotation matrices come in this format. Okay, so cos theta, negative sine theta, cos theta. Now I don't think this is in the formula book. I'll double check, but I don't think it is. So all we do is we match up each of the values in both matrices. So cos theta will equal, and I can see the first value in the matrix is negative root 2 over 2, and sine theta is root 2 over 2. Now if I do the cos inverse of each one of these, I'll get theta equals 135 degrees here, but I'll get theta equals 45 degrees here. So how do I choose which one it is? This is where we maybe use a sketch of the graph to help us. So if I start with a sketch of cos like this, now because cos theta is negative, negative root 2 over 2, what that means is that the angle theta must be bigger than 90 degrees, because this is where cos is negative. Okay, so the graph tells me that theta has to be greater than 90 degrees. Okay, so it's got to be the 135. But why did we get 45 from doing the cos inverse, of root 2 over 2 for sine, sorry, the sine inverse? So if I draw a graph of sine, I got a value of 45 degrees. So basically this root 2 over 2 is giving me this, but actually this is the angle that I want. This is the 135. My calculator told me 45. So if we get two different answers, use a graph of cos and sine to help you decide which one it's going to be. And because cos theta is negative, the angle theta has to be bigger than 90 degrees. That's why we settle on the fact that this is a rotation 135 degrees. Okay, and it will be an anti-clockwise rotation, so we get the same result, that it's 135 degree anti-clockwise rotation. So you can use this matrix here to help you decide on what type of rotation it is, and it will always be anti-clockwise. Now part B, we've got a square with these vertices, and we want to find the coordinate of the vertices of the image under the transformation described by M. So let's write the transformation matrix out, which is this, it'll be quite big, negative root 2 over 2, and then root 2 over 2, and then negative root 2 over 2, and then also negative root 2 over 2, like this. And then we're going to do a transformation of those points, so we'll write them in columns: 1, 0, 2, 0, 2, 1, 1, 1, like this. So we're going to multiply them together. Now, when we do that, and you could use your calculator to help you multiply them out, but by the time you've typed everything in, probably would have been easy to do it manually. So we end up with negative root 2 over 2, root 2 over 2 in the first column. Second column will be negative root 2 and then root 2. Then the third column is going to be negative 3 root 2 over 2 and root 2 over 2. And then the last column, let's just get this out of the way here so we've got a bit of space, is going to be negative root 2, 0. Okay, so we want to find the coordinates of the vertices of S now. So each column is the coordinate. So coordinate number 1, negative root 2 over 2. Then we have the second one. Oh, sorry. And then like the second bit of the coordinate. So that's coordinate number 1. Coordinate number 2, negative root 2. Let's write it out neatly. Negative root 2, root 2. Coordinate number 3, the third column, negative 3 root 2 over 2, root 2 over 2. And then the last column, negative root 2, 0. So this is where these coordinates end up. Right, now do exercise 7b on pages 134 to 136. So when you do these questions, remember, look at what happens to the points 1, 0 and 0, 1. And if it helps to do them in different colours, do it. Yeah, so see where this ends up. Let's just do this in black. So where does this point and where does this point end up? And those green and yellow represent 1, 0, 0, 1. So let's just highlight them in those colours so you can see. So that's the red one. This is the green one. And we want to see where they go. And it may be that you have a rotation, or you have a reflection, or some sort of enlargement, but we look at enlargements in detail later on. If it's a rotation, then any rotation anti-clockwise, then you can match up the values in this matrix: cos theta minus sine theta, cos theta, and then by matching them up, you can use that to help you work out what is the angle of rotation, the anti-clockwise angle of rotation.